So my name is Pietzuch. I'm faculty at Imperial College London in the UK. And what I would like to talk about today is a research project that we've been doing looking at a different programming model for big data applications. And this is sort of something that I guess has come up as a theme here during the summer school, that we've seen many examples for different big data processing systems, many different flavors of APIs with different features, different use cases. And this was sort of also our starting point for this work, and it actually very much fits with the motivation that Volker gave in his presentation on Wednesday, where he essentially argued that data scientists that have the right skills are a fairly rare animal, right? Because you need sort of quite a particular skill set in terms of algorithmic knowledge, but at the same time you also need some systems knowledge in terms of being able to use these kinds of tools that exist. So what we wanted to do is we wanted to create a big data platform that has all the nice properties that we've seen here. So it's scalable, it gives you support for real-time processing, it's fault tolerant, but at the same time it can be used by the largest number of people. And I'll explain what I mean by this. So in terms of the work that we've done, so it's kind of a combination of data management research and systems research. So a lot of the work that we do in my group is kind of at the intersection of both. And I think this is also a theme that we've seen here, that when you think about this entire big data space, even though it's so much based in the fundamentals of data management, large databases, query processing, and all of those techniques, since the systems that we're building are all distributed, you also need to have an understanding of distributed systems, fault tolerance, and a lot of the classical work that has happened in that space. And this work that we've done pretty much also very much fits at the intersection. So as I've mentioned, the motivation is that we want to enable big data analytics applications in many different domains, so including the kinds of examples that we've seen here over the course of the summer school. But at the same time, while we see that there are more and more people moving into this space, we also see that there's not the same increase in people who actually know how to use these kinds of technologies, right? So there's sort of more and more of a shortage of people that, for example, actually have real development experience with, the latest version of Spark or the latest version of Flink. And so one thing that we've also observed is that a lot of those problems, platforms, they're also moving targets, right? Because they're continuously being developed, so new API calls are being added, and that also makes it harder and harder to really keep up to date, because you may be able to use one particular version of those tools, but then sort of things move on, so you continuously need to stay up to date. So we wanted to have a programming model for big data that simply allows more users to create data analytics applications. Okay, so what do those users know in terms of languages? So you can look at one of those studies where people try to measure the popularity of different programming languages, right? So these kinds of things are probably not particularly scientific. I mean, they're often based on web search queries that people enter, or on the languages that are used for different GitHub projects. But sort of what you look at this, so in terms of the really popular languages at the moment, you see Java here, no surprise. C still going quite strong, C++ down here, Objective-C, obviously for mobile app development. Some really evil languages like PHP and Visual Basic, unfortunately, that don't want to die. But one thing that you can...
They're fault tolerant.
Well, PHP is a lot of things. Exactly. But actually, one curious thing that you can notice when you look at this list, they're all object-oriented or imperative languages, right? So if you're looking at this list, you actually don't find something that fundamentally is functional or declarative, right? I think actually SQL is missing from that list probably because it's sort of not a fully featured programming language. So SQL is probably one example of something that is declarative and actually has a large market share. But when you think about fully functional programming languages, so I'm thinking about things like Haskell or Camel or ML, I mean, they've been around for a very long time, but they also are niche languages when it comes to, well, hiring a software engineer and finding people who have that kind of skill. So maybe this is changing with languages like Scala that are multi-paradigm languages. So they actually have strong functional features baked in, and actually even Python has some functional features baked in. So maybe people have a bit more awareness of these kinds of languages. But that said, for example, Scala is not part of this list, right? So again, it's something that hasn't received large penetration. So this was kind of the starting point for our project, that we looked at, well, all the different platforms for big data applications that are out there, and they all follow some form of distributed data flow model that we've heard here a lot about. And they all then have a programming abstraction that kind of is functional and declarative, right? And there are a lot of good reasons for that. And we've heard about those reasons. So just to mention some, it really facilitates fault tolerance. Right? It makes it much easier to parallelize your computation, to reason about consistency, and it also simplifies issues such as query optimization, right? So you have a nice high-level declarative representation, so you can optimize. And these are great reasons to follow this kind of model. But that said, you then still have this large pool of programmers who you would want to create big data applications, and they have learned, well, languages like Java, MATLAB. I mean, they're imperative programmers, right? They don't necessarily immediately think about an algorithm that they want to express from a functional point of view, right? So there's a bit disconnect, and we ask, well, what can we do about this? So let's look at a particular example of what we would like to achieve. So let's take one of the examples that so again, sort of several people mentioned over the course of the summer school here, which are recommender systems, right? So there's sort of various algorithms that you can use. So let's say that you want to create a recommender system that uses collaborative filtering algorithm to then take essentially a stream of customer activities, so ratings on the website, and then it outputs up-to-date recommendations for what products people should buy. And so we want to create this application at scale, so we will follow a distributed data flow abstraction, right? So I could use a system like Spark or Flink and kind of think of the distributed data flow graph that enables me to then express that computation, right? And so I can run it on a cluster of machines with data parallelism. So now let's look at it from a programming point of view. So I've learned about collaborative filtering, and I would like to implement it in Java, right? So how would I implement it in Java? And the claim that I'm making is that if I've never heard about distributed data flow platforms, it would kind of look like this, right? So I would think, so how does collaborative filtering work? Well, it relies on two matrices, right? So I need one matrix, which I call the user item matrix, that simply records the ratings that users have provided on particular items. And then I have another matrix, which is my co-occurrence matrix. And that's the matrix that simply creates relationships between items that were rated similarly by different users. And this is what enables me to then provide recommendations, right? So I'm thinking about my main data structures that I need. I'm creating those matrices. And then I'm thinking about, well, what are the functions that are going to operate on those matrices? Well, I have two. I have one that is a function called add rating. And so whenever a user rates an item, that function gets called. What does it do? Well, it first needs to record that rating as part of the user item matrix. So it simply updates a cell within that matrix. And then I also need to recompute this co-occurrence matrix, right? So I have another function that simply takes this new this change to the user item matrix into account and simply updates my co-occurrence matrix. Right? So that's one function, so now I can read in new ratings, and then I have a function that gives me recommendations, right? So that's sort of the other part here. Again, how would I do this? Well, I would take a row from the user item matrix, that is the row for that particular user, and I simply multiply the co-occurrence matrix against that vector for which are the ratings for that particular user, right? So that's a straightforward matrix multiplication, and then I get essentially a custom recommendation vector for that user, right? So sort of a fairly intuitive way of writing that algorithm in Java, and the point that I'm trying to make here is that I would call this an idiomatic use of the language, right? I mean, this is sort of how we teach students Java programming 101, so think about the data structures, define them, think about the functions that operate over them, and that's it, right? So it should be fairly easy to understand this, this representation. So now let's look at how we would write this in Spark, right? So this is one example of collaborative filtering in Spark written in Java. So this is actually not the same algorithm, so this is a different method, and it's also only focusing on the part that provides recommendations. But the main takeaway here is that, well, it doesn't look like idiomatic Java, right? So what?
I mean, it's unfair because Spark is made for more Scala or Python.
Okay, so let's move on to the next slide. Let's look at the Scala representation instead, right? But I think my point, it looks much nicer, right? So we don't have this ugly, like, anonymous inner function craziness with generics. But I would still make the case that from the perspective of this imperative object-oriented Java programmer, that's still not quite idiomatic Java, right? Or it's not an idiomatic use of the language. Why? Because we've pushed a lot of the computation into the API, into those operators that we've defined, right?
But you didn't define the alternating list.
No, sure. So this is only essentially... it's only this part, right, that I'm kind of, right?
Enough to do the alternating.
No, sure. So, well, but then that example would simply end up being longer, right? There would be even more going on, right? But the point that I'm trying to make is that for somebody who is a Scala programmer, to really understand what that program does, they need to understand what the semantics of those operators are that are part of the Spark API, right? I mean, so here it's really obvious because, well, these are maps, and we have a join here. But then when you look at APIs, well, there are obviously more operators than that, right? So you're using a richer space, and now the business logic of your algorithm implementation is actually pushed into those operators, right? So you need to learn about them. It's a bit like learning a different language, right? You can't say that if you just read a textbook about Scala, you will understand exactly how to write Spark applications. No, you need to learn about Spark. There's actually another point.
Isn't it more, you see, the problem is that this has nothing to do with function or object-oriented. It's actually, it's about programming one element at a time or programming collections.
Right,
so
exactly.
Really question, I mean, even other language, even Java, they have collection libraries and they have things like stem libraries, huh? So it's a question, what do you teach a student when he starts programming?
Well, but okay, so this is actually the next point that I want to make. So this is the next difference here, is that what I've kind of lost in this representation compared to my earlier Java example is mutable state, right? So it's essentially, it's those matrices here that I've defined that I thought of, well, mutable data in-memory data structures where I can update any particular cell, right? And that's sort of how I thought about the implementation of my algorithm. Because in this representation, that's gone because I'm doing effectively bulk operations on collections, right? So again, we saw there are very good reasons why platforms like Spark and Flink are designed around this kind of abstraction. But again, it's something that from an imperative programming model point of view, it's not what you would expect, right? Because I can't simply create a matrix here and efficiently write a program that simply decides to update a small number of cells within that matrix, right? Because the whole programming model that I'm given for these platforms do not allow me to do fine-grained updates. It's all about bulk operations. And of course, pretty much most of the algorithms that I want to realize can be represented in this kind of way, so that's okay, right? But it may not be the idiomatic way of thinking about how to write my algorithm. Okay?
That's correct. Except just to mention again, the program that you wrote, that's a sequential one, actually you could write very similar one in Flink.
Okay, so Sure. I mean, hold on to that thought, because we'll be developing that program further, right? So just to kind of finish up that point, I mean, we've seen the reason why you have to do this in these kinds of frameworks, because effectively, a lot of the computation that distributed data frameworks consider is kind of stateless, right? I mean, you're doing bulk transformations with particular functions, and I mean, we've seen there actually some examples of having support for state, right? So we've seen this in the previous streaming talks where there were those synopses. So you have some way of having an accumulator or some mutable state, but ultimately the core of the programming model does not give you fine-grained mutable state. So instead what we wanted to do, so our goal was to essentially have an idiomatic imperative Java programming model and still have some of the benefits of writing big data applications, so supporting data parallel execution. So even though it looks like something that seems to be a very, a sequential program that you've written with fine-grained updates to state, you would still be able to execute this in parallel on a cluster of machines. And at the same time, we also didn't want to relax fault tolerance in this kind of world, right? So when you think about the design space of different systems, we wanted to have support for mutable state, and the other point is, and I'm going to talk much more about this, that we also wanted to have support for large state, right? It's easy to have a distributed data flow program where you have a small amount of state, you're keeping a counter. But let's say your state is actually the machine learning model that you're training, right? So then the state itself can be potentially hundreds of gigabytes of in-memory state that is actually distributed across your cluster, right? So this is where it makes it difficult. And at the same time, we wanted to also keep the nice properties of doing low latency processing, right? So this is what we've seen about having support for effectively a streaming model, and also we wanted to have support for iteration, right? So one of the drivers for this work was to efficiently support machine learning applications. So you kind of need to have iteration support baked in, right? So this was sort of the motivation behind this work, to kind of find a solution in the design space where we would tick all of those boxes. So our solution in a nutshell is that we've taken a data flow abstraction, and we effectively added state as something that you see when you represent a distributed data flow graph, right? So we call those things SDGs, stateful data flow graphs, where in addition to compute tasks that are stateless, you also have mutable state vertices within your data flow graph. And so once you have that abstraction, what you can then do, you can take a Java program that has been annotated in a particular way, and I will talk about those annotations more, but then you can, using static program analysis, actually take that Java program and simply translate it into one of those stateful data flow graphs. And this can then be done automatically by a compiler. And once you have a stateful data flow graph representation, then you can take and execute it on a distributed data flow framework, right? So we actually had to create our own distributed data flow framework because we had to have something that can manage the state, right? So it sort of has essentially mechanisms built in that allows you to then execute computation with mutable state while still dealing with things like elasticity and also fault tolerance. And we created an experimental system called SEEP that does this, that is essentially an execution engine for SDGs. So what I'm going to do in the rest of the talk, I'll first introduce this SDG abstraction, then I'll talk about the programming side, and I'll give examples how you can then take essentially this running example of the collaborative filtering algorithm, then add some annotations so that it can be automatically compiled into an SDG. And finally, I'll talk a bit more about the system side of the particular features that the execution framework has. And then I would like to finish with some experimental evaluation results to actually show you the performance that this particular approach can achieve. Okay, so what are SDGs? Well, so as I've mentioned, they're pretty much very similar to the types of data flow graphs that we've seen in Google Dataflow or in Flink. So you have tasks that do data parallel processing over data, and you have edges that are the data streams that are processed. And those data streams are also immutable. But then in addition, you also have what we call state elements, or SE. So state elements represent the state of the computation, and you can think of them as any in-memory data structure that you may have, right? So in the example that we've seen before, it could be one of the matrices that you need as part of your computation. And so state elements are mutable, and we have this constraint that we assume that tasks will always have local access to their state elements, right? So you always assume that this is an in-memory data structure that exists in the same machine where this task element is executing if it decides to update that given data structure. But we do permit state elements to be shared between multiple tasks, right? So multiple tasks can read or write from a particular state element.
Arrow means you can only read?
Exactly. So this is actually access. So this means read and write. This means only read access. Okay. So then there's one challenge here, and so the challenge here is that the state may become large, right? So obviously once you give a developer the ability to simply create a matrix and kind of use this as the bulk of their computation, the state itself may no longer fit into a single node, right? So now we kind of need to worry about the case, well, what do you do if you define one of those matrices and you have a very large number of users and items where it grows beyond the capability of a single machine? And at the same time, you need to make sure that you're scaling and you also remain fault tolerant, right? So remember that I've mentioned that one of the main reasons why early distributed data flow models were stateless, that it really simplified fault tolerance. So pretty much what you now need to think of the state elements essentially distributed state, and you need to have some kind of abstractions in that model to manage distributed state. So what are the abstractions that we have? Well, we have two. So we say that a state element can be partitioned, right? I mean, that's sort of the obvious thing to do. It's too large to fit into a single machine, but there's some kind of way of partitioning it by key, for example. Well, then you let the system simply partition the state across the memory of all the machines that you have in your cluster. But this is not possible for all algorithms. So there will be some types of state that there's no key. You can't partition it because essentially the access pattern is such that a task element needs to have access to the complete state. So in that case, we have something called partial state elements, which are essentially just replicated state elements with weak consistency. Right? And I'll explain both of those types in more detail on the following slides. Okay, so partitioned ones, I mean, they're pretty straightforward. So we assume that we have, again, an underlying key value model. So we have a key that we can use for partitioning, and then we apply essentially hash partitioning or range partitioning, the way we've seen it done by other systems. So in the example of collaborative filtering that we've seen, we can do this for the user item matrix, right? Because all the access in the program was always by key, where the key was the user, right? So we could decide to essentially hash partition or range partition by key. So in terms of the data flow graph, what that means that we need to split the stream. So we're partitioning the stream by the same key, and then we have the tasks elements that are accessing this partition state element, and well, we now have two partitions, and essentially as long as the stream is partitioned in the same way, then each task element again will only have to access its own local partition. So that case is pretty straightforward. What gets a bit more interesting is when you look at those partial state elements. So you do this whenever there isn't an obvious way of how you can partition your data structure, and in that case, you're replicating it, so now you have multiple replicas of the same data structure. And so the difficulty here now is that now you need to essentially specify which particular replica you're updating, right? So there'll be some operations in your computation where you only need to update a single replica, right? So we refer to this as local access. So you may have essentially a task element that will then only update its own local replica of that state element. But it turns out that once you have multiple replicas, well, at some point there will be some operations that will have to be applied globally to all of the replicas. Right? So therefore we also support in the model another access strategy which we call global access, where we can send data to all of the task elements that have a replica, and then that operation is applied to all of them. Okay, so we have essentially there's two different ways of managing those replicas. So actually, yeah.
Can you give an example where partial state elements are usually used?
Right. So I will actually. So the main example in collaborative filtering would be this co-occurrence matrix, right? Because in the co-occurrence matrix,
it's updated and has to be seen by everybody.
Exactly. So once I show you the Java code, you essentially see how this is mapped to the collaborative filtering example. Yeah.
Yeah, but this looks like more when you are doing stateless operations.
Mm-hmm.
This parallelism will give you higher throughput.
Yes.
But otherwise, then the partition states are more reliable for.
Yes. So the rule of thumb is that if you can use partition state elements, you want to be using partition state elements. Only if your algorithm is such that you can't partition your computation and effectively you're relying on global state, well then how do we make this scalable? Well, the only way is to replicate and then use weak consistency, right? Because if you replicate and use strong consistency, well then you're sacrificing scalability. So this is exactly what we're doing here.
So in one, let's say, in Fling we have this partition state element, but they don't have the
Exactly, right. But when you think about many machine learning algorithms, this is what you want. You want replicated state, but the algorithms can cope with a weak consistency model, right? And this is essentially what we're providing here. So the consistency that we're providing is that replicas are completely inconsistent, right? So they can be updated individually. But in your data flow graph, you can have special tasks that implement some kind of merge logic, right? So this is essentially like, you can think of it like a barrier that can reconcile different inconsistent replicas of your partial state element, right? So you can have application-specific merge logic that then has access to all of the replicas of a state element, can do some computation, and then generate some kind of consistent result out of those. Okay, so.
So we are talking about actually in the partial one. So this is quite big, so it's bigger than the capacity of one machine. And then we are replicating. So doesn't it?
So the idea with a partial state element is that each replica will fit in the memory of one machine. Why? Because in many applications, the updates will not affect all of the replicas, right? So typically, the size of a partial state element replica will grow more slowly over time, right? Which is pretty much when you think about training a machine learning model and you're replicating that model, you're essentially you're updating individual replicas with different data, right? So they are essentially disjoint, and sort of the overall model is essentially the union of all of your replicas, right? I mean that's kind of the idea here. So how do we reconcile partial state? Well, this is where we are collecting values from those replicas, and we effectively have a barrier that then feeds in those values into this task element that implements particular merge logic, right? So this now enables us to then reconcile the differences, and the output of this could then be used, for example, to reinitialize those replicas to make them consistent again, right? So you can think of this essentially as a synchronization mechanism, but it's quite a loose synchronization mechanism where, based on the requirements of the algorithm, you can specify when you want to synchronize, right?
I understand. The collect partial results, it's a barrier where it waits until it collects all the partial results from the node.
Yeah, but you can also have weaker barriers, right? So you can, for example, you could collect a subset of results, right? So in machine learning algorithms, you don't mind if you deal with stale data, right? So you may actually even have a stale view on some of the replicas. As long as there's some synchronization, probably the overall computation will still converge, and this is something that we do here.
Would you see a parameter server as a special case?
Yes. Yeah. So actually, so
sounds very much like
yeah. So actually, one thing that we're doing is we're using exactly that mechanism to implement a decentralized parameter server, right? Because yeah.
But these partial results should not fit in one machine. So how do
No, but this is what you kind of do when you're consolidating multiple machine learning model replicas, right? That you are effectively averaging, well, if the model, I know, is represented by a set of weights, you're averaging the weights, and actually the size of the combined model is small, well, is smaller than the union of all of the partial models, right? So we're taking advantage of the fact that this is something that is manageable again. Yeah. Okay, so coming back to collaborative filtering, so this is what the SDG looks like for collaborative filtering. So we have this user item state element, so this can be partitioned. And then we have this co-occurrence matrix, which we couldn't partition, but we can express this with partial state as part of that computation. So we're replicating it, but then we need to merge it when we're generating results. So I will show you the Java code for this in a moment, so you'll actually see what that merge how the merge logic fits. And sort of the inputs into those data flow are actually the two functions that I've showed you earlier, right? So one of them was, well, ingest a new rating, right, and essentially update the user item matrix and recalculate the co-occurrence matrix. And the other input, the other, well, stream source for this SDG is to provide a recommendation request, again, relying on the two state elements. Okay?
But still, I don't see, I mean, I know a little bit about I know I have this algorithm in mind for collaborative filtering where you use alternating least squares.
So this is
Where is it?
This is not alternating least squares, right? So this is
you have to iterate. Don't you?
no. So
I mean,
no. So this you see, right. So exactly. So this is essentially what people do when they express recommender systems in stateless data flow models. They essentially use a different formulation of the problem. For example, based on matrix factorization, so something that can be expressed within that model where the updating essentially results in a bulk operation. We don't have to do this here because we can essentially do fine-grained update to a matrix, right? So we can essentially use the straightforward realization of collaborative filtering where we're simply doing an incremental update to the co-occurrence matrix. We don't mind that we're reading in data and we've only updated 5 cells in that matrix, right? So this is why we can use a different representation. Okay. So this is an SDG for logistic regression, right, which is a machine learning algorithm for classification, and it sort of very nicely shows that you can now do iterative algorithms by having a cycle in the SDG. So what we're doing here, we are reading in items, we're training a model, so the model is represented as weights, so that would have to be a partial state element because you can't partition it. So you're replicating it, but the training can then happen in a data parallel fashion, and then periodically we're doing this merging to resynchronize our partial replicas, and then once we've merged the weights of all the partial replicas, we're feeding that back in so that each instance, each replica of that model can then be updated based on the globally consistent weights. Yeah.
So here you're not assuming that the weights fit in the memory of one machine, correct?
So we are, well, so it kind of depends how this part is implemented, right? Because, so we always assume that a partial state element replica will fit into the memory of a single machine, right? So essentially, so that, right. But then,
is that practical or not? I mean, he's a machine learning guy who was writing this. So.
Well, if you said only the partial ones fit,
yeah.
but not necessarily the whole weight vector.
Yeah, right, exactly. So, because, well, it depends what do you consider to be the entire model, right? Because you could think of this as the union of all of your partial models, or actually you can merge all of the partial models into something that you then consider to be the current model, right? And this is sort of what we are sending down this line, but this is actually done as a stream, right? So we're not, we don't need to materialize this in the memory of any particular node in our cluster. Right. So this is actually, when you think about it conceptually, this is actually very simple to using a distributed parameter server in terms of what we're doing, right? Where essentially the same assumptions fit. It's just a representation of the same idea as a distributed data flow graph. Right? Okay, so now, so let's move on and look at how this is then implemented as part of the Java source code. So I've mentioned that there's some annotations that we rely. And so the annotations essentially give us a way to disambiguate whether particular state can be partitioned or has to be replicated because there's no way of partitioning it. So here in the example, what you have to do if you want to use SDGs, you need to use this @partitioned annotation when you define the user item matrix to say that all access to that matrix is essentially based on a key, so therefore it's safe for the system to partition it. For the co-occurrence matrix, you now can't partition it, so you're defining it to be partial. Which now means that whenever there is an access, you need to disambiguate whether this is an access that only can affect a local replica, and you don't care which one, or it actually is access that needs to be executed against all of the replicas. So an example of access that needs to be executed against all of the replicas is when you get a new rating, you want to update the co-occurrence matrix on all of your on all of your workers, right? So you have this @global annotation that essentially now means that computation is executed on all of the workers, right? So all of the workers see the update to the ratings.
So all the workers do the
They will do this
operation.
exactly. They will do this in parallel, right? So this @global doesn't require any synchronization, right? So it's actually a cheap operation. No, because they're only applying the same update in parallel, right? The
There are many of these happening in the system.
Yeah, no, but they're, well, I mean, yeah, so you're reading in a stream of updated ratings, right? And all of the workers are applying it. Yeah. So what costs you, and then we're going to see this in a moment, is whenever you have a barrier because you're merging across your replicas, right? Question.
So here, when the programmer writes this code, so he needs to know in advance some approximation of the size of that matrix.
Yeah. Yeah. So, I mean, I think this is a very fair question because ultimately, well, so the question is, as a developer, do you still need to understand the size of those matrices and essentially the style of use to kind of get the annotations right? And that's true, right? I mean, this is sort of, ultimately what we're doing, we're taking a sequential program and we're creating a parallel version out of it, right? So there's no silver bullet to that, right? So you need to kind of be able to understand, well, how big are my data structures and how can I parallelize the computation, right? And this is what those annotations are for, right? Okay, and so we've got those annotations here. So then the only other thing that we're missing is this merging of results from different replicas. And the way we're doing this is that, well, so it needs to happen whenever we're providing a recommendation, right? Because the recommendation essentially needs to take advantage of the the replicas of the co-occurrence matrix across all of the nodes that we have. So now we are applying first this global operation where each node will multiply its replica of the co-occurrence matrix against the user row vector of the user for which we're providing the recommendation. And then we are getting a set of those back, right? So you can also think of them as partial state, right? Because each node in the cluster will have one partial result. And now we come to the expensive step, because to actually provide a single recommendation vector, we need to somehow reconcile those partial results, and that's done in an application, well, in a way that is specific to the given algorithm.
But does it mean that you broadcast the state?
Yes, so this is where a barrier comes in, right? So this is where we now have a task element that implements this merge logic, right? So now so this is sort of the first part in this example that actually I didn't show you before, right? Because before, when we had the purely sequential version of that program, we didn't need it, right? But now we need to provide this separate function called merge that now actually takes a vector of all of those partial results that were generated and implements essentially some application-specific merge function, right? So here in this example of collaborative filtering, you could, for example, average those vectors, right, and obtain essentially a single vector that is the average. Okay.
I just want to say, in a system like Spark, we have implicitly these two operators. They are called accumulator and broadcast variables.
Sure. I mean, so, right.
But they do it in the driver.
No, exactly. So, right, I mean, any representation of a machine learning algorithm that every now and then needs to effectively do a global synchronization will have to do something like this, right? So in frameworks like Spark and Flink, you will have specific operators that essentially do that, right? And they obviously limit then the scalability of your system, right? Because when you invoke them, you're adding a barrier, right? This is the same thing that we're doing here. I guess sort of one interesting thing is that we can have different types of barriers, right? So we can have weaker barriers that then improve the scalability for example, for particular machine learning algorithms.
And that's a particular interesting aspect. So actually, just as a point of reference, so in not really in Flink, but as a part of our research, we're actually also looking at some weaker barriers than the strict synchronization for this iterate operator.
Exactly.
Lines, So also implementing parameter server and concepts.
Yeah, exactly.
That's a very interesting thing we should
Yeah. Okay, so this is then the SDG version of collaborative filtering that you need to implement. So add those annotations, sort of reason about them. But then the, I guess, business logic of the algorithm pretty much looks like the original sequential program. So how does then the magic happen, the translation of that annotated program to an SDG? It's actually fairly straightforward, right? So what we're doing here, you can, for example, imagine how we extract the state elements that you need. We simply look at, well, what are the fields that are declared in your Java program that carry annotations, and we use those to then create the state elements. We can observe the control flow and the data flow in the Java program, and that gives us the structure of the data flow graph, right? So this tells us what the task elements are going to be. So these are simply the Java statements that then manipulate either variables or access the fields in your class that are the state elements. So we do some live variable analysis to understand when we create the streams that interconnect tasks, because potentially they end up on different machines, what's actually the data that we need to serialize and move from one node to another, right? But these are essentially fairly straightforward program analysis techniques, and we use an existing framework for Java to implement this compiler. And then finally, there's the code generation part. So now we actually extract the bytecode from the Java program that was written, and we use that to create the task elements and the state element data structures, and we then create essentially something that is a SEEP runnable, so that can be now executed by our runtime system. And again, we use fairly standard Java tools to do this, right? And it sort of happens entirely behind the back of the developer. They just invoke the compiler and they get something that they can run on SEEP. Yeah.
So how exactly do you figure out the logic of the operators of your tasks?
Right. I mean, so so if you go back to the program here, you essentially take the Java code that exists within a function, right? I mean, so pretty much a lot of the optimizations that were mentioned before for data flow graphs, like fusion of different tasks, I mean, they're also applicable here, right? You can decide, well, how big do you want that basic blocks to be? We actually have very simple heuristics that are guided based on how that code accesses state elements, right? So we ideally want all the code that uses a state element to end up on a single worker. But then if code uses different state elements, because we want to maximize the amount of memory, we put them onto different machines and then again put the code on the same machines, right? So these are heuristics. I mean, so you can't claim optimality, but sort of for the kinds of algorithms that we've been evaluating, that actually works reasonably well, right? So you get sort of a nice balancing between computation and the memory used for representing state. Okay. All right, so now I would like to move on and say a little bit about the implementation of the distributed data flow framework. So here we essentially faced two problems. So the first problem was, well, how do we deal with data parallelism now? So how do we, for example, provide elasticity features, well, very similar to what we've heard yesterday for Google Dataflow, where you want the system to automatically decide on the parallelization level for your computation. And the challenge that we have here is that we have the state, so whenever we need to, we are changing the parallelization level, we also need to partition or replicate that state, and all of that needs to happen transparently. The other issue is fault tolerance, right? So whenever any worker in our cluster fails, well, potentially we could also lose state, right? And we could also lose a large amount of state. So we need to think about the impact on fault tolerance that this has. So the approach that we've taken is fairly straightforward, that we have those state elements sort of as first-class citizens in our model, and we expose them to the runtime system, right? So the runtime system understands that this is a state element, and that's the state that is associated with it. So we can now have a framework define particular state management primitives that it can use to manipulate that state, right? To back it up, to recover it, or to partition it. And the nice thing is that once you have those state management primitives, you can actually define an integrated mechanisms that solves both of the problems that I've mentioned. So both scale out, so dealing with dynamic scale out elasticity, and also failure recovery by a combination of those state management primitives. So first of all, just to clarify, so what is state? So far I've only talked about the processing state, right? So the data structures that the program uses, like the user item matrix before. But in addition, we think of the state as any unprocessed data that exists in the Dataflow graph. And this is sort of where we're following very similar approaches from distributed stream processing systems, where we assume output buffers are essentially things that we don't want to lose. And we have a model where individual streams are ordered. They contain data items with monotonically increasing timestamps. So when I talk about state, I will always mean both the processing state in terms of the state elements on a node, but also those output buffers of data that essentially hasn't been processed downstream yet. So then we have three main state management operations. So one is to checkpoint. So we can checkpoint the state, and whenever we take a checkpoint, we associate it with a timestamp. It's actually a vector timestamp of the last processed data item per input stream, right? So we essentially understand how up-to-date that checkpoint is. We have a backup primitive that then stores the checkpoint on another node in our cluster, and we have a restore primitive that we can use to restore that checkpoint. And then we also have a partition primitive. So this is something that enables us to take a checkpoint and split it into two, right? So obviously, how to do this is specific to your algorithm, right? So because you have to decide on a partitioning key and a partitioning strategy, but we assume that the developer essentially tells us how to do this in a safe way for their particular algorithm. Right? So these are the primitives that we use. So there's some practical problems that we had to overcome when it came to the implementation. So for example, checkpointing is hard if your state is very large, right? Because it carries an incredible cost if you do it in a synchronous fashion, right? So obviously you can't stop processing to checkpoint, 64 gigabytes of main memory in Java. So instead the checkpointing needs to be done in an asynchronous way without acquiring any locks, so while the processing continues. And the way we do this is that while we're checkpointing, we're splitting the state element into two. So we have a read-only part that then can't be updated anymore. And we have essentially a copy that is the dirty state that we execute any writes against, right? So sort of a fairly simple kind of double buffering approach.
It's a versioning.
Exactly, right? Where now nothing touches the bulk of the state, so we can, in the background, serialize this and create the checkpoint, but the computation can still run, because any reads first need to be executed against the dirty state. If there's no data found, then you execute it over the state currently being checkpointed, and writes are only executed over the dirty state, right? So the cost that you pay, that after you're done with the checkpoint, you will have to reconcile the dirty state. But actually in most algorithms, that's a reasonable trade-off, because they're not dirtying state at a very high rate. So backup and restore, so there are sort of a couple of things here to say, is that if you have two tasks, A and B, so A is upstream to B and B is stateful, so has some state, so there's a stream here, some data items are being sent to from A to B and they carry a timestamp. A has an output buffer. It needs to buffer the data items. Right? So the data item is then transferred to B. It's now reflected in B state because B has processed it. So another data item comes along. It again needs to be stored in the output buffer. So then a couple of other things arrive in that output buffer. The question is, when can we actually discard data items from those output buffers? When can we trim them? And so one way of doing this is simply relying on checkpointing. So whenever we create a checkpoint of the state in B, the checkpoint will carry a timestamp of the latest data item that is reflected as part of that state. So if then A learns about that checkpoint because, for example, we back up the checkpoint to it, then it can also use that information to trim its output buffer because it now knows that though the result of the computation over those data items is actually reflected in the checkpoint, right? And so we use it as a way of trimming output buffers. The state partitioning primitive, again, nothing particularly surprisingly here. So we need to understand how to partition the state. So we can do hash partitioning, range partitioning. And so that enables the system to now split a checkpoint across multiple nodes and then also change the logical topology of the data flow graph so that then data items are still delivered in a consistent way. So now that we have those primitives, we can actually do both dynamic scale-out and failure recovery in a unified way. So how do we do this? Well, so if we assume two tasks, A and B, they're running on different machines, A is upstream to B, there are really two cases. So B could fail, in that case we need to recover it, or B becomes a bottleneck, in that case we need to partition the state or increase the number of replicas to remove that processing bottleneck that we have in the data flow graph. And so this is what we do, right? So when we want to recover, we rely on the backup of the checkpoints that we have. So if this node fails, we simply acquire a new node, and then we can use the restore primitive to then restore that checkpoint that we've created. And so one thing that we then need to do is replay any unprocessed data items from the upstream output buffer, right? Because the checkpoint is essentially out of date, so we need to now reprocess that data to bring the checkpoint up to date with respect to the rest of the system, right? But all of that can be done as a local operation. Scaling out is very similar because here again, we assume that there's a scale-out command, so we provision a new node, and then we use the partition primitive to then split the checkpoint into two. We restore it over those nodes, and then we also replay any of the unprocessed data items to bring the state up to date, right? So the nice thing is that all of this is done asynchronously, right? So actually you don't see any impact on the processing, you don't see any, you see small latency spikes while this happens, but we're not interrupting processing while this is being done, so it can happen entirely in the background. So when you look at our papers, there are actually much more tricks that you need to pay. So something that I didn't quite mention.
Which paper was this?
So I have the references at the end of the presentation. So if you're dealing with a large amount of state, then those checkpoints become very large, right? So you've checkpointed 64 gigabytes of memory, so actually even transmitting them to another node occupies a lot of network bandwidth, and you need to worry about the I/O cost of doing this. So actually what we're doing here is we're adopting an approach that is actually similar to what Spark is doing or RAM Cloud from Stanford, where we're doing parallel backup of those checkpoints and also parallel recovery. So whenever we've created a checkpoint at a given node, we are always partitioning that checkpoint, and then we're streaming those partitions to multiple nodes in the cluster where they're then written to disk. Right? So this way we're not occupying any memory to keep the checkpoints, and this is done in parallel, so we're using the aggregate bandwidth of those nodes. When we're recovering, we're actually partitioning the partitions of the checkpoints even further so that we can recover to more than one node. And the intuition here is that if you've lost a node in your cluster, well, essentially you've lost some processing capacity. So you've probably fallen behind in terms of the progress of your computation. So if you want to catch up, you need to add more resources to increase the processing rate. By recovering to a larger number of nodes than the number of nodes that has failed, we can essentially add resources to the system, and therefore in a streaming scenario, the system can catch up. Right? And this is what we're doing with this.
Trade-offs here, actually.
Sorry?
There can be trade-offs.
Mm-hmm.
The other system, they have no trade-offs because there is no state. Because you're already dealing with state,
Yeah.
eventually you're going to do state
Sure.
synchronization somehow.
Mm-hmm.
So maybe this partition will increase the problem later when you do state synchronization.
Yeah, I mean, so we don't need to synchronize across the partitions. I mean, the cost here is that we are dealing with those large checkpoints, right? And that's the cost that we're paying by essentially adding state to our data flow graph, right? But I guess
But you remember you had two types of state.
Sure.
The other was
Yeah. But well, sure. But this is sort of only the mechanism of how do you actually create the fault tolerance. Okay. All right. So I'm running out of time. So I guess I very briefly just want to mention a few evaluation results, just to convince you that having state in your data flow graph doesn't per se mean that you're carrying overhead when it comes to performance, right? So this is what we've done here. We've done a deployment where we implemented logistic regression, right? So essentially the data flow graph that I've shown to you before, and we compared to the performance of logistic regression implemented in Spark, right? So our formulation of logistic regression relies on mutable state, it updates the model, whereas the Spark one doesn't, right? Because it relies essentially on bulk updates of immutable data. And so we increased the number of nodes, we ran this on Amazon, and on the y-axis you see the aggregate processing throughput when we're training the model in gigabytes per second. And essentially what you see here from the result is that the scalability is actually very comparable, and also the performance of the two systems is comparable, right? I mean, there's some difference, well, because it's differently engineered systems. I mean, there's some optimizations that we've applied.
You are getting better.
Yeah, but then I wouldn't read too much into that difference, right? Because, I mean, they're definitely in the same order of magnitude. We used a particular version of Spark. It could have probably been tuned more. But the main takeaway is that even though we have all of this overhead of checkpointing, all the mechanisms that I've explained, we're still competitive in terms of the performance, right?
But
Because
it would have been very nice to see it with different model sizes. Huh?
with different model size, we figured. Well, I also
parameter feature size. Right?
yeah, I also have results on that. So. No. So we also explored that. So actually, well, maybe let me move to that result. So I'll skip over that. So maybe one other thing to mention here. So this experiment looks specifically at elasticity. So what we've done here, we used a benchmark called the linear road benchmark. That is a classical stream processing benchmark that has this property that as you run the benchmark over time, the stream rate increases linearly, right? So essentially to support that benchmark, you also need to increase the resources to your cluster. And the way the benchmark works, it simulates a network of roads where cars travel along those roads and they need to pay tolls. And essentially the benchmark specifies some queries that we've written as data flow graphs that then compute essentially some statistics over the tolls that cars need to pay. And so you have this SLA that the latency, the processing latency of results should stay low. So as your workload increases over time, you also need to effectively add resources to your data flow graph. So we deployed this on Amazon, and then we let this, so we executed this trace over time, and then what the red and blue line shows you essentially the input rate and the output rate of the system. And you see that the two lines are on top of each other because the input and the output rate follows the input rate. So as the input rate increases in that benchmark, what the green line shows you how we are essentially acquiring more and more virtual machines, so we're scaling out the data flow. And the scaling policy is really primitive. We identify a bottleneck and we greedily just duplicate the task instances for that bottleneck, right? So you see essentially how we're increasing the number of virtual machines. Then at some point we can't scale out any further because we actually become network bound on the input data sources. But we actually get a very competitive result for the benchmark, so a load factor of 350 with 60 virtual machines. A load factor of 512 is actually the highest published result for that benchmark on a kind of dedicated hand-implemented cluster, right? So even our system manages to actually come surprisingly close to that result. So maybe one last result to show, and this relates to Safe's question, that we also looked at sort of what is the cost when we deal with larger state. And actually the application that we've implemented here is actually quite interesting because it's not an analytics application. We created a distributed key value store, right? Because when you think about our model, we have fine-grained mutable state, right? We can deal with input streams. So those streams could be simply key lookups in a distributed key value store. And this is what we've done. So we are increasing the size of a key value store by scaling over more and more nodes. And then we're measuring, and this is the red line here, the throughput that we get when we're handling read and write requests over that, right? And as one would expect, because here we can partition our state element perfectly, we get linear scaling, and the other axis shows the access latency, and the access latency also stays very low, right? So
now, depending on the algorithm, you might have a barrier.
Exactly. So this is actually something that you can see on, well, this result that I've skipped over. So this was actually an evaluation of collaborative filtering, where we looked at the performance when you change the read and write ratio, right? And as you remember, for the reads, we need the barrier, right? So the more reads you have, when you look at the throughput slowly decreases because that's the cost of the barrier that you have to pay, right? So obviously, there's no magic, but if you have computation where there is a sensible way of partitioning the state, then the system scales in the linear way as you would hope. Okay, so just to wrap up, so what I try to do in this talk is kind of give you an idea that there are also other types of programming models that are worth exploring. And what we've taken is a really extreme position where we wanted to have something that is imperative and has mutable state, right? I mean, so I'm not saying that this is strictly better than declarative models where you can apply sophisticated optimizations, but it's simply a different point in the design space when you think about how we should program systems like this. But the main takeaway from this work is that even if you have a Dataflow representation that has mutable fine-grained state, it doesn't mean that you need to pay a performance cost for this, right? Because you can still have an approach where you do failure recovery based on essentially this combination of log-based recovery on checkpointing that we've done, and you can implement it in a way where it actually has a very low runtime overhead, right? And we know how to do these kinds of things. So even a system like this can then get very competitive performance, but you now have this richer data flow abstraction that not only deals with immutable data streams, but also deals with mutable state. So a prototype implementation of SEEP is available on GitHub. So essentially everything that I've talked about, you can run. And the main publications that summarize this work, so we had a Sigmo 2013 paper that more talks about the state management and the elasticity and recovery. And then we had last year Usenix ADC paper that talks about the programming model and essentially the translation of regular imperative Java programs to stateful data flow graphs. Okay, thank you very much.
Thank you.